Okay, now this is the first questions in deformation of solids. A mass of 200 kg is suspended from the lower end of a vertical rod of diameter 0.4 centimeter. The elastic limit is 1.4 exponent 8 Pascal. When the mass is removed, will the rod return to its original length? Assume that the cross section does not change. Okay, this one assume that the cross section means the area does not change. Area remains constant all the time. Okay, so we have the mass suspended from the rod. Okay, this is the mass, and the diameter of the rod, elastic limit. Okay, what is elastic limit? So elastic limit is, you see, this one is the unit Pascal. Pascal is the unit for stress, But elastic limit means this one. You see this one? B is a point B we learned before, the elastic limit. This is the point B is the elastic limit. So the stress limit, the stress for this elastic limit is given by 1.4 exponent 8. So 1.4 exponent 8 is this one lah. Yeah, 1.4 exponent 8. For the stress for that elastic limit is 1.4 exponent 8. So this question is asking that when this mass 200 kilograms suspended from the rod, pulling the rod, is the stress applied to the rod more than this elastic limit or less than this elastic limit? So that is what we want to investigate. If the stress applied is more than the elastic limit, then the rod cannot return to original length. But if the stress applied is less than this elastic limit, then it only undergoes the elastic deformation, and surely it will return to original length. Okay, so let us investigate this one. Okay, so we have the mass suspended. So it's something like this one. Okay, vertical rod. So this is the vertical rod. Okay, this is the vertical rod, and this is the mass applied for 200 kilogram. Okay, and this is 200 times gravity. Okay, not moving, stationary, so acceleration is 0. So the force exists in the rod is the tension. Tension. Okay. So yeah. So this is the information given. We have the mass, we have the diameter of the rod, and the elastic limit, or we call the stress limit. This is 1.4 exponent 8. From diameter of the rod, we can get radius. Radius is divided by 2, 0.2. Centimeter must change to SI unit. Centi is -2. Okay. This is the rod actually. Yeah, this is the rod it mentioned. This is the rod actually. It's actually like a cylinder, it's actually a cylinder hanging the mass. Okay. So first of all, we can find the cross-section area. Okay, cross-sectional area, because we have the diameter. Let's find out the cross-sectional area of the rod. We need it. Okay, we find that there's a radius. So let's find out the cross-section area. So radius is 0.2 exponent -2 square. So what is the cross-section area? 1.2566 exponent -5 meter square. That's the cross-section area. The rod. That's the cross-section area we have found. Yeah, it's a circle. The circle. That's why we use pi r square. Circle section area. Now we need to find the tension in the string. Okay, tension in the string, which is also equal to because this one is in equilibrium, no acceleration, so tension equal to mg. Okay, let's find out the tension. 200 kilogram times 9.81. So what's the tension in the wire? 1962 Newton. Okay, now we have found the tension inside the rod. Okay, this tension is pulling on the rod. Okay, or expanding the rod, the tension. So we can find the stress that exists inside the rod. Okay, so the force, remember this one. The force that exists in the wire or the rod is always the tension. It's always the tension, not the mass, not the mg. It's the tension. Okay. So it is tension over area. Okay. So 1962 divided by cross-section area 1.2566 exponent -5. Okay, or in SI unit, this one is Newton, this one is meter square. So the answer I get is 1.56 exponent 8 Newton per meter square, or you can write Pascal. This is the stress. This is the stress experienced by the vertical rod. Yeah, this is the stress that experienced by the rod now. Okay, due to this tension. Okay, because of this tension, this rod is under this stress, this amount of stress. Okay, tension divided by the cross-section area, pi r square. This area. Okay, so tension divided by cross-section area, pi r square, you get 1.56 exponent 8 Newton per meter square, or Pascal. Stress. This is the stress in the rod now. So is this stress over the elastic limit? The stress limit is 1.4 exponent 8 Pascal. Oh, the stress experience is 1.56, but the limit is just 1.4. That means the limit now is 1.4, but the stress is 1.56 exponent 8 Pascal. This is the stress. So the stress is above the limit. So it is over the elastic limit. So it cannot return to original length. It will undergo a plastic deformation. Because it's over the limit. So what I can write is this one. Finally, I discover that this stress is more than the limit. Yeah, or I can write as more than the stress for elastic limit. Okay, so it exceeded the elastic limit. So I must write down the value I got just now, 1.56 exponent 8 Pascal, more than the limit of only 1.4. It's more than. So that means when it's more than it, so it undergo plastic deformation. So when you have plastic deformation, means rod will not return to original length. Okay, rod will not return to original length because of plastic deformation. Okay, it's more than the elastic limit. Okay, so when talking about elastic limit, always will refer to the stress. For this case, this is the limiting stress. Yeah, and the stress for the elastic limit. This is the limit, means the elastic limit. Okay, I got the stress more than the elastic limit. So plastic deformation will not return to original length. Yeah, the rod will have permanent extension. It will stay at the shape after it extend. It will stay at the shape. Yeah, it will not return to original shape. Okay, that's all for the first question. So stay tuned for the next one. Yeah, bye.